Hey everybody, welcome back to chemistry, and we are continuing on with chapter 7 in the gas laws. And so in this presentation I want to cover some more gas laws and some other information to help you solve problems that are this information being derived from these gas laws. And so the gas laws I want to cover are the combined gas law, which is talked about in section 7.4 in your book. Also, I want to next cover Avogadro's law, which is in section 7.5 and 7.9. The ideal gas law, which is in section 7.6. Then there is a way that you can take the ideal gas law and identify other gas laws from it. I want to explain to you how to do that. That's also in section 7.6. And then finally, we'll talk about how the ideal gas law can be manipulated to help you find information about gas density or its molar volume. And this is in 7.8 of your book. Okay, so here we go. So let's talk a little bit about the combined gas law. So I have it there on the screen, and so the thing that you'll notice is kind of similar to previous gas laws, but a little different. So the way it's similar to previous gas laws is what we used to do is we would have a gas at some kind of initial condition, say we'll call it condition 1, and then we were relating to it the gas at new conditions, we'll say condition 2. So that is still there when we see this combined gas law. But here in the combined gas law, instead of seeing two variables being related to one another, now we're seeing three variables. And so those three variables are pressure, volume, and temperature of a gas. So we can relate those three variables at a new condition from the gas at the original condition, as long as we understand that that gas is not changing its number of moles as you're going from that original condition, condition 1, to the new conditions, condition 2. So one thing to notice about this law is basically it's a fusion of some of the earlier laws we were looking at that had two variables in them. So one thing you can see in there in that law is that there is Boyle's law in there, which is P1 V1 equals P2 V2. On top of that, you can sort of see superimposed on that is Charles' law, which is V1 over T1 equals V2 over T2. And then Adamanton's law, which is P1 over T1 is equal to P2 over T2. And so that, when they're all fused together, gives you the combined gas law. And so one thing you'll have to do when using this gas law is if you have a temperature in something other than Kelvin, you will have to convert it to Kelvin. So most of the time in these problems, you'll have a temperature in Celsius. And so if that is the case, then just add 273.15 degrees to get it into Kelvin. So probably the best thing to do is for me to try a problem like this on the board, and I'll give you some tips to solving this. Okay, so we have a gas that occupies 10 liters at 240 degrees Celsius under a pressure of 80 kilopascals. At what temperature will the gas occupy when it's at 20 liters if the pressure is increased to 107 kilopascals? And so looking at this problem, what we can see is that we have three pieces of information, three properties, which are the volume, the temperature, and the pressure of the gas. And so let's see if we can define some initial conditions and then see what we need to solve for in the new conditions. So the volume initially is 10.0 liters for this gas. The temperature is 240 degrees Celsius, and so I'll have to convert that to Kelvin in just a second. The pressure is 80.0 kilopascals. Okay, so let's see how we can define the variables in the new conditions that we're going to bring this gas to. It says at what temperature? So it looks like we're trying to find T2. So that is the unknown in this problem. Let's see, we have a new pressure, P2, which is 107 kilopascals. And then we have a new volume, V2, which is 20.0 liters. Okay, so we're trying to find T2. So I think what I'm first going to do before I derive the appropriate equation that we can plug in numbers to is just first, let's just take this initial temperature at Celsius and convert it to Kelvin, sort of like as I was doing it before. So what you do is you add 273.15, and kind of like I pointed out before, we'll get a calculator answer, which is 240 plus 273.15. So the calculator answer I get is 513.15. But I think at this point, what I want to do is solve this problem in the way that the book does it. And what the book does is when you have a temperature, the first thing you do is get that into the correct number of significant figures, and then once that's done, plug it into the equation and then solve. So we have 240, and there's a decimal here, so the uncertain digit in 240 here is in the ones place, so this has 3 significant figures. The uncertain digit here in 273.15 is in the hundredth place, and so there are 5 significant figures here. And so again, the calculator answer will be 513.15, but you might recall the rules for adding numbers for significant figures. And so here, the number we should get should be rounded to 513 with its uncertain digit in the ones place. Okay, so this will be in Kelvin, so I'll put a K here. Okay, so the next step is to go ahead and solve this equation for T2. So let's see if I can do that. So it's going to be P1 V1 over T1 is equal to P2 V2 over T2. So this can be a little tricky deriving these equations for the variable you want to solve for, but what I'm going to do is I'm going to take T2, which is the denominator here on this side of the equal sign. If I want it in the numerator, I have to put it on the other side of the equal sign, so it goes up here like this. And so what we can do is write that out, see what we got now. So we have T2 P1 V1 over T1 is equal to P2 V2. And so the next step is we got to move out the other variables so that T2 is by itself. And so we're going to move P1 V1 from this side of the equal sign, and it will go into the denominator. And it goes to the other side of the equal sign. And T1 here, we have to move out as well, and it goes to the other side of the equal sign. It will go in the numerator like that. And so what I get is T2 is equal to P2 V2 T1 over P1 V1. So I think that's correct. Okay, so let me just go ahead and plug in some numbers and just confirm that the units cancel as expected. So P2 is 107 kilopascals, and V2 is 20.0 liters. And we also have T1, which is here. It's going to be 513 Kelvin. And then over P1, which is 80.0 kilopascals. And then we have, it looks like V1, which is 10.0 liters. So let me see what number I get here when I get this. And so I get 107 times 20 times 513 divided by 80 divided by 10. So the number I get on my calculator is 1372.275. The book again suggests that at this point, after you plug the numbers into the equation, you get a number from the equation. You should round this to the correct number of significant figures at this point. So it looks like, if you check carefully, this number needs to be rounded to 3 significant figures. So here are 3 here. Here's the uncertain digit. We'll look to the right of that. It's below 5, so we do not round up. So what I get is 1370. With this 7 being the uncertain digit, this 0 is not significant. And so remember, this is in Kelvin. So the final step is, I think the problem is asking what temperature it should be. Now, it doesn't say it has to be in Celsius, but let's just calculate into Celsius. So it's minus 273.15, and let's see what we get. So I get 1370 minus 273.15. And so I get 1096.85 on my calculator, But again, we have a significant figure furthest to the left here, and this number here compared to this, uncertain digit here, and compare this uncertain digit here. And so we have to round such that the answer has an uncertain digit here in the tens place. And so we look to the number next to it, and it's above a 5, so we round up. So this rounds up to a 0, and this next digit becomes 1. So I get 1, 1, 0, 0 degrees Celsius, with this 0 being the uncertain digit. So this has 3 significant figures. So if you wanted to, you could write this as 1.10 times 10 to the 1, 2, 3 degrees Celsius. And I think that's the answer I got on the screen. It is. Okay, so we will move on. Okay, so the next problem I'm just going to point out, I'm not going to solve it, but I encourage you to try this problem on your own. And so you use the combined gas law to solve this problem, which is P1V1 over T1 equals P2V2 over T2. So I encourage you to stop the video for a moment and just try that on your own. Okay, so now we're getting into a new law. And so the new law is called Avogadro's law. So it's actually pretty easy to understand. And the reason is because we do this quite a bit in our lives. We have seen examples of Avogadro's law by blowing up a balloon. So imagine that you have a balloon that's just out of the package and is relatively deflated. Now, you know that balloon will have a little bit of air inside of it. That air in that deflated balloon causes the balloon to have a certain size, and so it has a certain volume. Now, you know if you blow up the balloon, what are you doing? You're basically taking the amount of air that is inside there, which is measured in a certain number of moles, and you're just adding more moles to it. So when that happens, you take that balloon, you're increasing the number of moles. And what happens is that you know that when the moles of air in that balloon increase, then the volume also increases. And so this will happen as long as the temperature is kept constant and the pressure remains constant. And so this is sort of basically Avogadro's rule, is that when you have some kind of flexible container that can hold a gas, if you increase the number of molecules or the number of moles in that container, you're going to have to increase the volume of that container as long as you keep temperature and pressure of the gas constant. So in a sense, what you can sort of see is that as the number of moles of the gas increases, the volume of the gas increases. And so what that says is that the number of moles is directly proportional to the volume of the gas. And so what we can do is we can write that in a pretty simple equation, that V is proportional to N. Now, what you might remember is if you wanted to, you can turn that equation into an equality as long as you add some kind of numerical constant. So if V is proportional to N, you can also write V is equal to a constant K times N. And then if you wanted to, you could solve for the constant K. And so what that equation is basically saying is that whenever you have a gas, assuming that pressure and temperature are constant, that the volume is always going to be proportional to the number of moles it has. And so if you wanted to, you can sort of derive an equation from that. And that equation would be, again, looking at a gas at initial conditions, which is condition 1, versus a gas at final conditions, condition 2. And you can see that that proportionality of volume versus the moles will just remain the same versus from the initial conditions to the final conditions. And so that'll be V1 over N1 is equal to V2 over N2. And again, this only really applies if the pressure and the temperature are constant between these two conditions of 1 and 2. So again, this is Avogadro's law, that if the number of moles of a gas increases, that the volume increases. And so I kind of just talked about this a moment ago, the explanation as to why there is Avogadro's law. And again, as you know, that when you increase the number of molecules or moles of a gas in a container, its volume must proportionally increase if the pressure and temperature stay the same. So let's go ahead and try a problem using this relationship. And it says, let's say you have a large balloon with 0.35 moles of gas that has a volume of 8.56 liters at 25 degrees Celsius and 1 atmosphere pressure. If you were to add 1.0 mole of gas to this and the temperature and the pressure remain the same, what is the new volume? Okay, so let's go ahead and see if we can solve this problem here. So let me just write out what the initial conditions are. So here we're given an initial number of moles of gas, which is 0.35 mole. And we're also given an initial volume. V1 is equal to 8.56 liters. Now, just a note, we're also given a temperature and a pressure. So let me go ahead and write this here for the moment. So the temperature is 25 degrees C, and the pressure is at 1 atmosphere. Okay, this says, if you were to add 1 mole of gas and the temperature and the pressure remain the same, what is the new volume? So we have new conditions where we're adding a mole to the gas that we already have 0.35 moles of. So N2, after you add that mole to the original number of moles that is there, we should have 1.35 moles of gas for N2. So what we're trying to do is find the new volume that this gas occupies now after it receives another mole of gas. But the temperature and the pressure in these new conditions is the same as it was in the original conditions. And so if that's the case, we don't have to really worry about that in the problem. So we can just erase that. And so if we know a relationship between moles and volume, we can figure out what the answer to the problem is. And that relationship is Avogadro's law. So we again know that the moles of a gas at initial condition divided by the volume of the gas at that initial condition is going to be equal to the moles of the gas at the final condition divided by the volume at the final condition. And so what you can do is solve this equation for V2. So to do that, I'm going to move V2 to the other side of the equal sign here. And so I have V2 is equal to N1 over V1 is equal to N2. And so I need to get V2 by itself. And so to do that, I have to move N1 and V1 to the other side of the equal sign. So V1 in the denominator here goes in the numerator. N1 in the numerator here goes in the denominator. And so I get V2 is equal to N2 times V1 over N1. I think that's probably correct. And so what we can do is go ahead and plug in numbers. And so V2 is equal to N2, which is 1.35 mole, times V1, which is 8.56 liters, over, and it looks like N1, which is 0.35 mole. So what I'm kind of hoping we'll see is that you can sort of look qualitatively at this problem, that if we're adding moles of gas to the gas that's already there, we would expect the volume to increase. So let's just hope that we get out an answer that is larger than the original volume of 8.56 liters. So let's see, it's 1.35 times 8.56 divided by 0.35, and I get 33 liters. So yay! So that is consistent with what we would expect, that when you increase the moles of the gas holding the pressure and temperature constant, that we would expect the volume to increase, and that's what happens. So that appears to be the correct answer. So we will move on. So another thing you sort of need to understand is you're going to see problems where you may have to take a gas at initial conditions and then figure out what a property of the gas is at something called standard conditions. And so what standard conditions are a particular pressure and a particular temperature. And so at standard conditions, the pressure of the gas must be average atmospheric pressure, which is 1.0 atmosphere, which is 760 millimeters of mercury. And the standard temperature would be 0 degrees Celsius, which is 273.15 degrees Kelvin. Now, another thing that's kind of useful to know is you should understand what volume any gas occupies if you have 1 mole of it at these standard conditions. meaning you have 1 atmosphere pressure and 0 degrees Celsius. It's always the same volume no matter what gas you have. At standard temperature and pressure, 1 mole of any kind of gas, it could be oxygen, nitrogen, a mixture of gases, it doesn't matter. 1 mole of any gas occupies 22.414 liters of space. Now again to note, 1 mole will occupy that particular volume only at standard temperature and pressure. So for example, let's say you were to increase the temperature of that gas. And so 1 mole would occupy 22.414 liters of space at 0 degrees Celsius. But you remember from Charles' law that if you increase the temperature, you're going to increase the volume. So for example, if you were to double the temperature in Kelvin, you would double the volume. And so that 1 mole of gas would no longer be 22.414 liters, it would be a much greater volume. So again, this number, 22.414 liters of volume, only applies for 1 mole of gas when it's at its standard conditions of pressure and temperature. Okay, so here's kind of an interesting application of that to Avogadro's law and to solving problems. So let me just go over an example here. So I want you to note here I have an equation for the formation of ammonia. And I want you to notice that all of the molecules, whether they be reactants or products, are in the form of a gas. Now, you already know how to interpret the coefficients of that equation, and so that you can see that 3 moles of hydrogen will react with 1 mole of nitrogen, gives you 2 moles of ammonia. Now, again, just note that all these molecules are gases. And so if we wanted to, we could figure out, knowing what the molar volume of the gas is at standard temperature and pressure, we can take those moles of gas and multiplying by the molar volume of 22.414 liters per mole, calculate how much volume these moles of gas would occupy. And so I'm doing that there in this equation, that 3 moles of hydrogen times 22.414 liters per mole is the molar volume. And so what you can see is that when you do that multiplication, for example, of hydrogen, you get 67.2 liters. When you do that for nitrogen, you only have 1 mole there in that equation. You multiply by 22.4 liters per mole, you get 22.4 liters. And so for ammonia, you have 2 moles there. You multiply that by 22.4, you get 44.8. But what you might notice is that all these numbers reduce to the original mole ratio. So when you see an equation and all the molecules are gases and you see the coefficients in front, not only do those coefficients refer to moles, but they also refer to volumes. So if 3 moles of hydrogen reacts with 1 mole of nitrogen to give you 2 moles of ammonia, you can also say that 3 volumes of hydrogen reacts with 1 volume of nitrogen to give you 2 volumes of ammonia. And so an example of volume here would be liters. And so you could say 3 liters reacts with 1 liter to give you 2 liters, or if you wanted to, you could use different units. It could be 3 milliliters reacts with 1 milliliter to give you 2 milliliters. So just to note, if you have an equation and you have molecules that are gases, the mole ratios are also volume ratios. And usually people think of that in terms of liters, although you don't have to. So let me just give you an example of how to use that knowledge to solve a problem. It says, according to the reaction equation, and again, it's the one we just were looking at, how many liters of ammonia would be produced when 5.6 liters of hydrogen reacts with an excess of nitrogen? So here we have 5.6 liters of hydrogen. And from that equation, what we want to do is figure out how many liters of ammonia are produced. Well, a simple way to solve that problem is to recognize that when you see that mole ratio between hydrogen and ammonia, which is 3:2, that is also a volume ratio or a liter ratio. So we can also say that 3 liters of hydrogen produces 2 liters of ammonia. And so you can use that ratio to set up a fraction there to help you solve the problem. And so what I've done here is I've just set up the fraction of 2 liters of ammonia to 3 liters of hydrogen, and then I flipped it in such a way that the liters of hydrogen cancels out, and so we get an answer in liters of ammonia. So that liters of ammonia, 3.7 is what you would get from 5.6 liters of hydrogen. Okay, so let's go ahead and solve a few problems using this relationship that can be very helpful. And it says the problem we have here now is calculate the volume of liters occupied by 7.40 grams of ammonia at STP. Okay, so here what we have is we have 7.40 grams of ammonia. And so what I want to do is I want to get this into, it looks like into liters of ammonia. So eventually we want to get this into liters of ammonia. So how will we solve this problem? So let me kind of write this out down here. So here we have grams of ammonia. And so what you can probably imagine is whenever you have grams of a molecule, you probably just want to immediately convert it to moles of a molecule. So grams of ammonia can be taken to moles of ammonia. But in the end, we want liters of ammonia. We don't have so much an equation here, but what we can do to solve this particular problem is we can convert moles of ammonia to liters of ammonia pretty easily because we're at standard temperature and pressure. So remember, when we're at standard temperature and pressure, that 1 mole of any gas occupies 22.414 liters of space. And so we can easily convert moles of ammonia to liters of ammonia knowing that. So grams to mole is just the molar mass, and then moles to liters of ammonia is molar volume, which is, again, 1 mole of any gas occupies 22.414 liters of volume. Okay, so what we can do is we can go ahead and solve the problem. So first, let's convert grams to moles. So we have the molar mass is given to us, so it's times 1 mole of ammonia over, and it looks like the molar mass is going to be 17.03 grams of ammonia. And so the next step is we got to convert moles of ammonia to liters of ammonia. And so let's think of some ratios we can write using this molar volume. We can write 1 mole of ammonia over 22.414 liters of ammonia, or we could write the reverse of that. So which one do we want to use to solve this problem? It looks like we want to use the reverse of this, right, to get an answer in liters of ammonia. So let me just give myself a little bit more room here. There we go. So it's times 22.414 liters of ammonia over 1 mole of ammonia. And so let's just confirm that the answer is going to be in the units that we want. So grams of ammonia cancels here, moles of ammonia cancels, and so we get an answer in liters of ammonia. And so I think if you work out the math and correct the answer to the right number of significant figures, it's going to be 9.74 liters of ammonia. So just to point out again that we can use this ratio of 22.414 liters of ammonia here to 1 mole of ammonia because we just happen to be at standard temperature and pressure. If the problem was dealing with other conditions of pressure and temperature, like say 2 atmospheres at 100 degrees Celsius, then we could not use that ratio to solve the problem. Okay, so let's move on to the next problem. Okay, so we have another problem here. So according to the reaction equation, and it looks like it's the reaction of formation of water from hydrogen and oxygen, if we have 2 liters of hydrogen react in excess of oxygen gas at standard temperature and pressure, how many grams of water are produced? Okay, so let me go ahead and write this equation out. So we have 2H2 plus O2 gives you 2H2O. And so we have 2 liters of hydrogen gas. And in the end, what we're trying to do is figure out how many grams of water are produced. So it's grams water. So there are actually 2 ways to solve this problem. I'm going to show you both ways. And so one way you can solve the problem is you can take the 2 liters of hydrogen, and because we are at standard temperature and pressure, we can convert this to moles of hydrogen using the molar volume of 22.414. And then once you're at moles hydrogen, you can convert that to moles water using the mole ratio. And then once you're at moles water, what you can do is convert this into grams of water using the molar mass. So let me go ahead and write that out really quickly. So here we want to get this into, I guess we want to get this into moles of hydrogen. So it's 1 mole of hydrogen over the volume that this occupies at standard temperature and pressure, which is 22.414 liters of hydrogen. So that's fine. So now what we can do is, now we have moles hydrogen, we can convert this to moles of water using the ratio of 2 moles of hydrogen to 2 moles of water. So it's going to be 2 mole of water over 2 mole of hydrogen. And then what we can do is the final step is convert from moles water to grams of water using the molar mass. So it'd be times 18.02 grams of water over 1 mole of water. And so I think if you work this out, you would get the answer 1.61 grams. So let me show you a second way you can solve the problem. And so the second way would be this. You can start out with 2 liters of hydrogen again. But remember what I was telling you earlier is that these coefficients not only indicate a mole ratio, but because the molecules you are comparing here, hydrogen and water, are in the gaseous state, you can also think of this coefficients as being a volume ratio. And so you could choose the volumes to be units. So if you wanted to, you can take the 2 liters of hydrogen and using the ratio of 2 liters of hydrogen reacting with excess oxygen gives you 2 liters of water, you can figure out how many liters of water that would be. And then from the liters of water, using the molar volume because you're at STP to figure out the moles of water, and then moles of water using the molar mass to get the grams of water. So really quickly, it would be like this. It would be 2 liters of water over 2 liters of hydrogen. And again, the ratio here is 2 to 2. So again, these coefficients here not only apply to moles, but to volumes. Then what you have is you're going to have to get this into moles of water. So 1 mole of water is equal to 22.414 liters of water because we are at standard temperature and pressure. And then the final step would be to multiply this by the molar mass of water. And so I think if you could do it this way and you should get exactly the same answer. So either way will be fine. Okay, so let's move on to a new concept here. Okay, so I need to talk a little bit about what the ideal gas law is. So one of the things you've learned previously is that when we think of a volume of a gas and its pressure, if you change the volume of the gas, the pressure will change as well, but they're inversely related. So if you increase the volume of a gas, the pressure will go down. If you decrease the volume of the gas, the pressure will go up. They are inversely related. And again, you're assuming that here you're holding the moles and the temperature of the gas constant. We've also learned about Charles' law in that the volume and the temperature of gas are directly proportional. You increase one, you increase the other. And here, in this case, you would have to keep the moles and the pressure of the gas constant. Avogadro's law is the relationship between the volume and the moles of the gas, and so they are directly related. Again, increase one, increase the other. Avogadro's law applies when you hold pressure and temperature constant. Now, if you wanted to, you can sort of combine these proportionalities into one equation. And so I've done that there. And you can see that volume is going to be directly proportional to moles, which is N, and temperature, but inversely proportional to pressure. And so one of the things that you already know is you can take that proportionality between volume and NT over P and turn that into an equality if you add some kind of numerical constant. So I've done that there, and here I say V is equal to constant times NT over P, and now we're not going to call the constant K anymore. We give it a special letter. We're giving it a capital R. So V is equal to R, which is the constant, times N times T divided by P, and then you can sort of rearrange variables, and then we sort of get the common expression of this new gas law we're going to deal with, which is PV is equal to nRT. And so this law is called the ideal gas law. So the thing to sort of note about the ideal gas law is it's a little bit different than the gas laws you sort of used in the past. With the gas laws you used in the past, usually in the problem what you would have is you would have some initial conditions, and then what you wanted to do was define a property of the gas maybe at some new conditions. But here it's a little bit different. Here we're just looking at a gas at the same conditions. And here within those conditions you may be given, say, 3 properties. For example, you might be given, say, a volume or moles and temperature of the gas. And from those properties at those conditions, you just find the pressure. So here this is used a little bit differently. And that you're only going to sort of figure out what one property of a gas is from the other 3 properties when you're at the same conditions. Now, one of the things you need to worry about is the value of R, and so that will be given to you on a test. But just to note that this constant, this R, which is in that equation, can have different values depending on what the units are going to be in that equation. So for example, if you're given, for example, a volume in liters and you're given a pressure in atmospheres and you have moles and a temperature in Kelvin, R would be equal to 0.08206. However, in a problem, if you were given a volume not in liters but in milliliters, but you had atmospheres in Kelvin, then R would be a different value. It would be 82.06. You might, instead of having pressure in atmospheres, you might have it in a different unit like kilopascals, and then R changes its value again. And so there are all these different values of R depending on what the units are for the properties of the gas. And so the best way to sort of deal with that in a problem is probably just use this first value of R, which will be given to you on a test, which is 0.08206 liters atmospheres over moles degrees Kelvin are the units for the constant. And so if you are given a problem, you can use that value of R if you take each of those properties of the gas and make sure they are in the appropriate units that you see there. So volume must be in liters, pressure must be in atmospheres, and temperature must be in Kelvin. And then there's going to be some kind of amount of gas which will hopefully be in moles. So let's go ahead and do a practice problem given that information. So what we have is we have sulfur hexafluoride is an odorless, colorless, very unreactive gas. Calculate the pressure in millimeters of mercury exerted by 1.82 moles of the gas in a steel vessel at 5.4 liters at 72.5 degrees Celsius. Okay, so let's go ahead and assign some variables here. We're going to try to find the pressure of the gas. So I'm going to put a question mark here. We have the number of moles of the gas, which is 1.82 moles. And so it's contained in a vessel, and so the volume of that vessel is 5.40 liters. And then the temperature of the gas is 72.5 degrees Celsius. So I think what you can sort of see with this problem is we have initial conditions here, but we don't have new conditions that we're converting this gas to. We're looking at the initial conditions, and given we know the moles of the gas, the volume of the gas, and the temperature of the gas, can we find the pressure of the gas? And the answer is yes, we can using the ideal gas law. And so the pressure here is P times V is equal to nRT. And so we can solve for P using this law. And so R, let's just write this out, it's 0.08206, and the units are liters, atmospheres over moles, degrees Kelvin. So what we have to do to use this formula is we have to make sure that we have all these properties in the correct units. So volume is in liters, which is good. We have an amount of gas in moles. We will have to convert this temperature into Kelvin. So it's going to be plus 273.15. And again, I'm going to use that trick that the book does where we work out what the temperature is in Kelvin by adding 273.15 and then rounding it at this point to the correct number of significant figures, plus 273.15. And so I get on my calculator 345.65. But note the uncertain digit in 72.5 is here. The uncertain digit in 273.15 is here. And so here, I think this is going to be 345.7 rounded to the correct number, significant figures. And this is in degrees Kelvin. Okay, so at this point, what we can do is we can plug this into the ideal gas law. But first, let me go ahead and solve this for P. So you can work it out on your own, but P should be equal to nRT over V. Okay, so let me go ahead and just plug in numbers here and see what we get. N is going to be 1.82 mole. R is 0.08206 liters, atmospheres over moles, degrees Kelvin. And then, let's see, the next thing we need to have is T, which is 345.7 degrees Kelvin. And then what we have finally is volume, which is 5.40 liters. And so let me just confirm that the units cancel as expected. So moles here cancels, liters cancels here. We have an Kelvin cancels, and so we're left with atmospheres in R. And so when we plug in these numbers into PV equals nRT, we'll get a pressure in atmospheres, which we'll have to convert into millimeters of mercury. So let's go ahead and work that out. So it's going to be 1.82 times 0.08206 times 345.7 divided by 5.4. And I get for a pressure 9.56. I'm going to round this to correct number of significant figures at this point because that's what the book does after you plug in numbers into the equation. So there should be 3 significant figures. So I get 9.56 atmospheres. Now that's not the answer. We really had to convert this into millimeters of mercury. So I'm going to multiply it by 760 millimeters of mercury. I think these 3 digits are considered significant. Over 1.0 atmosphere. 1 is an exact number. And so what do I get? I get times 760. And so I get, rounded to the correct number of significant figures, I get 7270, should be 3 significant figures, millimeters of mercury. And if you wanted to, you can convert this into scientific notation. So that should be the answer there. Okay, so let's move on. Okay, so one of the things you can do is you can take the ideal gas law and derive all the other gas laws from it. And so let me just give you sort of an example of that for taking the ideal gas law and deriving the combined gas law from it. So this is how you would go about doing it. So you write out the ideal gas law twice. So here I'm doing it for condition 1, the initial conditions, which is P1 over times V1 equals N1 times R, the constant, times T1. And then you write next a bar, and then you put in the final conditions underneath the bar in the denominator. So it's P2V2 is equal to N2RT2. So let's say we write that out, and we want to write out an expression that relates the pressure, volume, and temperature of gas in initial conditions compared to the final conditions. But keep in mind, if we're comparing these 3 properties in these 2 different conditions, what we're doing is we're going to look at the 4th property, which is moles, and we're going to keep that constant. So what you do is, keeping in mind that moles remains constant, and the value of R, which is a constant, that remains the same number as well, so it's constant. So what we can do, well, let me back up just a touch. Okay, so here what we can do is, I'll get to that in just a second, but here what I'm just sort of doing is separating this equation into 2 portions, and so there's an equal sign in the middle. Now what I want to do now is just go ahead and we can cancel out the R from this equation because the R value remains constant whether the R is in the first equation or the second equation. It's the same number. And then here we're holding moles constant if we're looking at the relationship between pressure, volume, and temperature of a gas between these two conditions. And so if the moles are constant, that means the moles in the initial condition, N1, is going to be equal to the moles in the final condition, N2. And so that can be canceled out. And so after you cancel out the property that remains constant and that constant R, this is what you're left with, is P1 over V1, say that again, P1 times V1 over P2 times V2 is equal to T1 over T2. What you can do is move variables around, and then that is there on the right, the combined gas law. And so, again, what you can sort of see is that if you write out the ideal gas law twice under two different conditions, put the first condition in the numerator, the second condition in the denominator, if you cancel out the variables that remain constant between these two conditions, you can derive the relationship between the other variables in these two different conditions. So let's go ahead and solve a problem where we're doing that so you can sort of see how this is applied. So you have 2 moles of a gas at 2 liter volume in a flexible container, and it's at 1 atmosphere pressure. Let's say you add 1 mole of gas to this flexible container and the pressure increases to 1.2 atmospheres and expands to a new volume. Assuming the temperature does not change, what is the new volume of the container? Okay, so this help me get my bearings here. What I want to do is assign variables, and that can help me focus as to whether I know a gas law that can be used to solve the problem. Okay, so we have initial conditions where we have moles, we'll call it N1 is 2.00 moles. And then we have volume of a gas, so it's V1 is 2.00 liters. And we have a starting pressure as well. P1 is equal to 1.00 atmospheres. Okay, so far so good. Let's say you add an additional 1 mole of gas to this flexible container, and the pressure increases to a new pressure, 1.2 atmospheres, and expands to a new volume. What is the new volume of this container? Okay, so we now know some new conditions. So the new number of moles at the new conditions, N2, will be, it looks like we're going to take the original number of moles and add just another 1 mole to it. So the new number of moles is 3.00 moles. We're trying to find the new volume V2, right? And also, what we are given the new pressure, which is 1.2 atmospheres. Okay, so we're basically trying to find V2. Now, I think you can sort of see, at least right now, I can't think of a gas law that I can immediately apply to this that I know of that could solve for V2. And the reason is, when I think about Boyle's law is relationship between pressure and volume of a gas in 2 different conditions, given that temperature and moles is constant. We cannot apply that here because in this problem you can see we have pressure and volume changing, but we also have the number of moles changing. So what we have to do is we have to derive a new expression that relates the pressure, volume, and number of moles of a gas at these 2 different conditions. And we're going to have to derive it from the ideal gas law. So let's go ahead and try doing that. So the ideal gas law is P1V1 is equal to nRT1. Let me put a 1 here by the moles here. And so we're going to divide that by P2V2 is equal to N2RT2. So what we're going to have to do is we're going to have to derive an expression between volume, pressure, and moles of a gas at these 2 different conditions. And so to go ahead and do that, let's cancel out the variables that remain constant. So one variable that remains constant is R. Another variable that remains constant in this problem, according to the problem, is temperature. That does not change. So we can sort of write this now like this. Let me get a new pen. So it's going to be P1V1 is equal to N1 over P2V2 is equal to N2. So what I can do further is break this up into two portions like this. P1V1 over P2V2 is equal to N1 over N2. Now, what we want to do is we want to compare initial conditions to final conditions. So let's get the initial conditions on one side of the equal sign, the final conditions on the other side. So I'm going to move N1 here to the denominator on the other side of the equal sign. I'm going to move P2V2 here in the denominator to the other side of the equal sign. So let's see what we get. So we get P1V1 is equal to N1, or divided by N1 is equal to P2V2 divided by N2. Okay, so it looks like we can use the expression to solve the problem. So what you would have to further do is you would have to solve this for V2. So I'm going to have to move the N2 over to the other side of the equal sign, goes in the numerator, and the P2 I'm going to have to put on the other side of the equal sign in the denominator. So what I get, I'm going to write this over here, is V2 is equal to P1V1 times N2 over P2 times N1. So let me just kind of plug in numbers really quick and let's see if we get the right answer really fast. So it's 1.00 atmospheres is P1. Volume 1 is 2.0 liters. And so N2 is 3.0 moles, and it looks fine so far. P2 is going to be 1.2 atmospheres, and N1 is 2.0 moles. Let's see if we get the correct answer here. Hopefully we do. So it's going to be 1 times 2 times 3 divided by 1.2 divided by 2. So I get 2.5, and I think all the units cancel out in such a way that should give you liters. And so that should be the answer. Okay, so let's move on to a new problem. Okay, so the final thing we need to go over is the relationship between the molar mass of gas and its density. And we can sort of figure out the relationship between those two variables using the ideal gas law. So here I sort of take the ideal gas law and derive a new equation that relates the molar mass of gas to its density. But I think the thing for me to do is to go ahead and write that equation here on the screen. All right, so the equation is as follows. And so you might remember the ideal gas law is PV is equal to nRT. So you could derive this new equation if you want to. I'm just going to give it to you. So it's P with the weird looking M that looks like this is equal to dRT. So P is pressure for a gas. M here, this weird looking gas, weird looking M is the molar mass of gas. And so you know the units for molar mass are grams per mole. And then D here is density of a gas. And so the units here are a little something that we haven't seen before for density. They're not grams per milliliter, which is what we're used to seeing for density, or grams per cm cubed. They are grams per liter. Okay, so the way I remember this equation, I think of nighttime dirt. So nighttime PM, DRT, dirt. Nighttime dirt, and that helps me remember what the equation is. Okay, so let's go ahead and use this equation to solve some problems. So I've got a problem here. It says calculate the average molar mass of dry air. In other words, air with no water vapor in it. If it has a density of 0.0117 grams per mil at 21 degrees Celsius and 740 millimeters of mercury pressure. Okay, so essentially what we're going to try to do is we're going to try to find the molar mass of the gas given its density, and we know its pressure and its temperature. So let's first assign variables and see where we're at first. So the density is, we have a value for that which is 0.00117 grams per mil. Okay, so remember when we use this equation that relates density of a gas to its molar mass, we have to take any density and get that into grams per liter. So we would have to convert this. So it'd be 1,000 milliliters per 1 liter. And I think if you work that out for the density, it's going to be 1.17 grams per liter. Okay, so that's good. So we have a pressure of 740 millimeters of mercury. Okay, so when we use the equation PM dirt, we have to get the pressure into atmospheres. And the reason is because our value of R is still the same. Our value of R is liters, atmospheres, moles, degrees Kelvin, so the pressure here must be in atmospheres. So it's going to be 740 millimeters of mercury times 1 atmosphere over 760 millimeters of mercury. And so the millimeters of mercury cancels out, so it's going to be 740. Let me work this out really quick. Divided by 760. 740 divided by 760 is going to be 0.97. I'm just going to round it off now, as the book suggests, 0.974 atmospheres. And then the next step is we have to get temperature probably into Kelvin, unless it's given to us in Kelvin. Is it? No, it's not, unfortunately. So it's 21 degrees Celsius plus 273.15. And so I get 21 plus 273.15. I'm going to round this. Two significant figures at this point. So it's 294 degrees Kelvin. Is there any other information we need? R, of course, is 0.08206 liters, atmospheres, over moles, degrees Kelvin. Okay, so what we would have to do to solve the problem at this point is do a little bit of algebraic manipulation and solve this equation for M. So I'm going to do this really quickly. So M is equal to dRT over P. And then at this point, it looks like you just plug in numbers. So let me just go ahead and throw in the numbers. So we have, again, density must be in grams per liter. So it's 1.17 grams per liter. R is 0.08206 liters, atmospheres, over moles, degrees Kelvin. And then finally, we have a temperature. It looks like I'm going off the screen here, so I'll just write it up here. The temperature is going to be 294 degrees Kelvin divided by the pressure, which is going to be 0.974 atmospheres. And so our answer should be 29 grams per mole. So let me just confirm that the units are going to be in grams per mole. So we can see that atmospheres cancels, Kelvins cancels. It looks like we have grams per liter and liters per mole. So it looks like liters cancels. And so we will have an answer it looks like in grams per mole. So I think when you do the math, and it turns out to be 3 significant figures, it should be 29.0 grams per mole. Okay, so let's move on to a new problem. Okay, so we're going to do one more problem using this equation. And so this is a kind of a neat problem because what you can see is we don't have a lot of numerical information here, and yet we can use this equation and the conditions of standard temperature and pressure and still give us an answer. So what is the density of nitrogen gas at standard temperature and pressure? So again, we're going to use this equation, which is PM dirt. So the pressure times the molar mass of the gas is equal to density of gas times the gas constant times the temperature. So let's go ahead and solve this now for D and see where we're at. So density of the gas is equal to pressure of the gas times the molar mass over R times T. So let's see if we can sort of find numbers for these variables and see if we can get an answer for that. Okay, so I think it won't be too difficult to do. So if we're at standard temperature and pressure, we know what P will be. So I'm just going to write that in. So it's going to be 1.00 atmospheres. The molar mass, even though that isn't given to us in this problem, what we can do is we know the identity of the molecule. And since we know the identity, we can figure out what the molar mass for that molecule is going to be. So it's diatomic nitrogen. Each nitrogen atom has an atomic mass of 14.0 grams per mole. You can look that up in the periodic table. So if we have two atoms, and so the molar mass for N2 should be 2 times 14, which is 28.0 grams per mole. So I'm just going to write that here, 28.0 grams per mole. And then over R, which is 0.08206 liters atmospheres over moles degrees Kelvin. And then T, what you would have to do is at standard temperature, which is what we're at, that's 0 degrees Celsius, we have to get that into Kelvin, so that's 273.15 degrees that you add to 0. And so that's going to be rounded to correct number of significant figures, 273 degrees Kelvin. So I think if you go ahead and plug in those numbers, what you would do is you get 1.25. And so if we wanted to, it's not a bad idea to see if the units cancel in such a way that leaves us an answer in the units that we want, which is grams per liter. So atmospheres cancels here, moles cancels here, temperature cancels here. So it looks like we're good so far. So we have grams left in the numerator, liters in the denominator, so it's in grams per liter. Now, let me show you a second way that you can solve the problem, which is kind of interesting. If you can remember this relationship, it only applies at standard temperature and pressure, but it could be useful in quickly solving a problem where you have to find the density of the gas. That relationship is as follows. The density of the gas at standard temperature and pressure is equal to the molar mass of the gas over the molar volume at standard temperature and pressure. And so let's go ahead and quickly see if we get the same answer but using this equation. So we are at standard temperature and pressure. We know what the molar mass of the gas is. It's 28.0 grams per mole. The molar volume of the gas at standard temperature and pressure is 22.414 grams per liters. Okay, so if you do the math here, I think what you'll find is 1.25. But let's just confirm it's in the units that we think it should be. And so what you can see is grams in the numerator here cancels out with grams in the denominator. We're left with an answer in moles per, whoops. Let me try that again. It's going to be 28.0 grams per mole over 22.414, and it's going to be liters per mole. See, dimensional analysis saves me. Okay, so what you can see is that the moles cancel, and so we should get an answer in 1.25 grams per liter, which should be the answer. Okay, thank you for listening, and we will see you next time.